In this chapter, we will look at the how actually apply how actually we apply the biasing into the amplifier. So far we just learned that how we replicate the current source. In actual amplifier, we have a variety of uses. For example, like this current source load, and such current source load can be implemented with the PMOS current source there. Why? So some of the students may be confused with the implementation of such kind of thing with the NMOS current source. For example, if you implement that I1 with NMOS, what happened? As you know that NMOS is the source. If we have a current direction like this, the bottom is the source and this is the gate. So whenever there is the voltage change and current change on the M1, that will create the voltage fluctuation there. If we have a voltage fluctuation on the source node of the MOS, that will create the current variation. So this is not the current source. It would be rather just the register, small signal register with each impedance is 1 over Gm. So if we have a PMOS device there, this is the drain. So drain voltage doesn't change the current level through the PMOS. That's why we use that PMOS device as a current source in this example. In differential pair, we have a current source, tail current source that can be implemented with the MOS device. As I explained before, in this case as well, any voltage fluctuation on the drain side doesn't affect the current level ideally. So this is the right way to implement the current source in the amplifier example. In actual circuit, there are many places uses the current source. It can be either pull down current source or pull up current source, right? So such kind of current generation coming out of the reference current generator. So we have a golden reference current. Golden reference current is given. So we will discuss how we generate such reference current later, but for now we just assume that such current is available. So if that such reference current is available, then we have a current meter on the NMOS current meter and the PMOS current meter kind of things. We can generate as many current source as you want, right, using the bias voltage, right? So this is quite useful. This is more complicated example. So starting from I reference current, the size of this diode connected device is W over L. If I have a 2x larger W over L, then this branch will flow to 2 times IREF, right? IREF. And also here 5 times larger than the device, so this IT will be what? So 5 times IREF, right? So for the same size of a left and right hand side, will flow this equal amount of current, 5 over 2 IREF, both branches, right? So here IT this is the IT, same as the 5 times IREF. If the M5 flows the zero point 0.4 IT, if we want to design that way, then what we can do? So zero point 0.4 IT, and this device will flow like how much? 0.1 IT, right? Because of the symmetry on the left and right, right? Half of the IT will flow on the left, right? So this is like this, and then what it means that so this branch is 2x larger, so total, okay, this is total 2.5, so the 20% will flow on the right, so the left hand side branch current, let's say 0.4 versus 0.2, so 5, so 0.4 IT is equal to what? So that would be the 5 over 2 times IREF times 5 over 4 over 5, right? So finally IT, we can find that 0.4 2 IREF 5 times IREF, right? So IT is the 5 times IREF. Oh yeah. So the what happened? So the 0.4 IT is the what? How much? The 2 IREF. So this one must be 2 IREF. But on here is 2 IREF. So we have to have a same device size for those two to replicate the same current level, 2 times IREF, right? So this is W over LP. What about the device size M3? So M5, 5 device size is W over LP. What about the M3? M3 device size should be that just need to be sized. This is not the current source, so this one has a designer's freedom to choose the device size that will determine that the output load impedance 1 over GM3. So designer's choice. To choose 1 over GM3, right? So we have identified the device sizes here, M5, M4, and M5, right? M5 device size. So this kind of calculation is required in order to design the right size of the device to support the right amount of current, okay? For example, if you want to generate the 2x larger reference current, then you have to choose a 2x larger device size. As I explained before, so having 2x larger W need to be considered by this physical fact. For example, if you have a size of the W devices shown in here, on the side view, actual polysilicon is fabricated like this, and if you make this device 2x larger device like that, the edge effect, this edge, the silicon polysilicon at the edge actually poorly define the value of a W. So if we want to have a 2x larger W, we have to draw the 2x W, but actual device characteristic may not scale properly. So device controlled properly by W. So one way to do that is that the better way, so we use the same device dimension like this and multiplicate in parallel like this. That will actually bring us the 2x larger W, 2W device size, right? So as you can see here in this schematic, if this single transistor flows IREF, then each single transistor on the right will flow the same amount of IREF because it is sharing the same VGS, right? And the same size, W over L. So this is how we replicate the current level. So you can expand this kind of a technique. Instead of having single device, you may use multiple devices like this in the reference generator. If we have a 2xW over L is the unit, 2W over L is unit, then if we have 4 times 4 device unit devices will create the 2x larger IREF, because the half of the current will flow onto the left and another half will flow through here. So you can have this, and then if you want to have a half device current, half IREF, then you can have a single device size like this, right? So that you can have a fractional current also can be generated. This can be happen by split devices, meaning smaller finger size, device size. Another way to generate the fractional current level is that, let's say you start with a single device, then if you series connected, then it is actually effectively increasing L, double L. So because we are relying on the same device characteristic and dimension, we can safely generate the half IREF by this technique. So on the left hand side technique or right hand side technique, both are available. Whenever you need anything, then you can have a design freedom to go ahead with the left hand side approach or right hand side approach. Okay. This is a typical common source amplifier. We will have an input at the gate, but we need to provide the proper bias voltage, which that will set up the VGS. So we need to ensure that we have a VGS, VTH plus overdrive voltage. Once that is set up, we are adding our signal tone on top, right? So this is something that we want to have. This is VB, right? So how we generate this kind of voltage reliably. Typically, if you want to add voltage, you cannot directly add voltage. For example, if you have a voltage source in here, V1 and V2, can you add those two voltage like this? No, right? This will not work because this is the ideal voltage source. We cannot, if there is any voltage mismatch there, infinite amount of a current I will flow. That's not going to happen. That can be expected from the relationship between voltage and current, any voltage source and current source. Here, let's say V and I. So this is V0 characteristic like this. So in order to make sure that the voltage drop across the voltage source is V0, it can flow any amount of current. It can go up to infinite amount of current, minus infinite. Any current level can be supported to make sure the voltage drop across the voltage source. So if you have a different voltage connecting like this kind of structure, will result in infinite amount of current, so circuit will break. The only way to add voltage is kind of on placing that on top, like V1 and V2. In that way we can guarantee the output voltage is V1 plus V2, right? So what about in this case, how we achieve that such kind of a voltage addition, like VB plus Vin? That's something that we wanna consider or think about more in detail. Okay, this is one of the example to bias the CS common source amplifier stage with R and C. So here VB is directly coupled, directly connected to the gate. Because the input to the gate is infinity, the input impedance is infinity, only capacitive, right? We have the CGS only. So there's no current through the RB, meaning the voltage drop is 0 volt. So any voltage you apply on this node will appear on that. So VB is here, right? So we can find the proper bias voltage from this resistor. So RB, but here is large, and IRB equal always 0, and VRB equal 0, right? Second, the CB, if you make the CB large, any voltage fluctuation will be added onto X. Why? Because this is the high pass filter network. So we have a high pass filter network. So V in, so V out, so VB. This is a high pass filter. So as long as the as long as the signal V input frequency F in is greater than bandwidth. What it would be the bandwidth? 1 over 2 pi RB CB, right? But actually we have the CB plus RB. So if the signal frequency is much higher than the high pass filter cutoff frequency, then your signal will be loaded onto that to the gate. Okay, so the beauty of this biasing scheme is that the DC is provided by VB. Then on top we have the AC comes out. So VX node like this, and V in node, it can have any common mode voltage. So this is V in. So V in has we can separate. So by having this AC coupling, this is called AC coupling. This can separate a input voltage, input common mode CM, and the VGS bias, so VB. So you can choose any VB and any input common mode voltage level, right, by having this AC coupling. Okay. Now the question is how to generate the proper VB. So how to generate the properly. We use the current meter. So our goal is to make sure that the current from the M1 is something that desired the value. So we have a reference IB here, current meter here, and that if and then we connect that through the RB, because the current going into the RB is always zero, right? So the voltage appeared on here will be always the same. So we have the same voltage across the RB. So RB voltage drop is always 0 volt. The same VGS is shared, so if you have a current meter IB, then you can make the IB, right, for the same size of the W over L, right? This is something that you can utilize. Typical on-chip realization, the on-chip capacitor like CB, if you want to implement that in on-chip, the CB can range in the order of a few femtofarad, a few picofarad. That would be the maximum kind of in a range that realistic. The area is there. So for if you if you limit the size of the CB because of the area requirement, then the thing that you have to change is the RB. So RB must be maximized in order to pass our signal and load that onto the gate of the transistor, because such kind of a network shown in here has the bandwidth of the 1 over RC CB, right? So if the maximum CB, so this is F and of 0 dB, let's say this is 0 dB, then the typical characteristic would be like this, right? So this is the 3 dB bandwidth, that is 1 over B CB. So for the limited CB size, in order to design that proper WB, the RB must be maximized. But for the large RB, also consume a large area as well, because typically register is implemented in polysilicon. So you have to connect many polysilicon in series like this, right? This is quite large area. To minimize the area consumed by the RB biasing resistor, we can use that large resistor with the triode transistor shown in here. So as you know, our own register in triode can be defined by mu and COX W over L the overdrive. So if you can design that overdrive so small, right, then you can increase the R-on. So also you can have the small device size, right, and small V overdrive that would can implement that the large R. This is kind of, but the drawback out of this kind of a transistor implementation is that the register itself is nonlinear, right? So register value, if there's any voltage fluctuation there, then we have a VGS variation, meaning overdrive voltage variation. That means the R on also fluctuate whenever there's the input signal activities there, right? And also this is the 1 over GM impedance, right? So there will be some fluctuation voltage drop across the VDS, right? So such kind of voltage fluctuation results in the large register variation. So signal can be distorted. Might be distorted. That means our input signal range might be very small, right? For proper amplification, the linearity must be satisfied for certain application. So such kind of requirement must be double checked before you actually utilize this kind of circuit. So this is just useful for very low frequency application. So now the question is how we properly generate the VG for this kind of biasing. We want to have a very small overdrive voltage between gate and source, right? Here. So the gate and source happen, as I explained before, the terminal the source and drain terminal changes depending on the current flow. So for this transistor, the DC current is 0, but AC current still flow, right? AC current flows. So the direction determines the source node, right? So current direction. The source node. Okay. So now how we properly generate the VG, we'll see in the next slide. Shown in here, this R is the realization of a large R on register here. So to have a small overdrive voltage, we stack the transistor like this. If there's any current flows like IB shown in here, there should be always turn on. This stacked device MC must be always turned on, right? And each overdrive voltage will be set by this current level and the device size. If you make this device size very large, that will result in the small overdrive, right? So IB equals to half mu n COX W over L V overdrive square. From this relationship, if you have a large device size, then we will get the small overdrive to support that fixed current level, right? So by having this sizing properly, then we can realize the proper amount of on resistance, RB, this is a bias resistor, right? That should be, typically that should be large, right? So large RB is possible. So for the different process and temperature, if the VTH changes, the beauty of this kind of scheme is that for VTH changes, you will track the variation. VG will track, right? So VG tracks the VTH variation. For PVT from PVT variation, right? So this can be a reliable realization. So this kind of application is used in some place like audio application, because such kind of application require very low frequency signal. Is low frequency signals are handled like in the order of tens or 20 kilohertz range there, right?